Hello, geometry folks. Today we're going to be talking about inscribed or in a circle, angles that are created in a circle, and inscribed polygons or polygons that are inside of a circle with all its endpoints touching the circumference of the circle. So what we're going to need today is our notebook. There is no foldable, sadly, a pen or pencil, and also a calculator. So with that, we'll get started. So before we do some examples or any theorems or anything, let's obviously start with some vocab or some definitions. So an inscribed angle is an angle whose vertex is on the circle and whose sides contain chords of the circle. So in our picture, our inscribed angle would be the angle BCD, or this angle right here. So notice that its vertex C is on the circle and its sides or segments CB and CD are chords of the circle. Another term that we need to know is the intercepted arc, or the arc that lies in the interior of the inscribed angle and has its endpoints on the angle. So the intercepted arc of the inscribed angle would be arc BD. So when we say the interior of the angle, this is the interior of the angle, and the arc lies between the points B and D, which are the endpoints of that angle. And so I just want to make sure that we know what I'm talking about when we say inscribed angle and intercepted arc before we do some problem solving within circles. Okay, so the theorem that we want to talk about knowing inscribed angles and intercepted arcs is that there's a theorem for the measure of an inscribed angle. If an angle is inscribed in a circle, then its measure is half the measure of its intercepted arc. So given the circle BAC, where the angle BAC is the inscribed angle and the intercepted arc is BC, we're saying the measure of angle BAC, or the measure of this angle, is going to be equal to half the measure of the arc BC in degrees. So that's an important theorem that we need to know. So make sure you get this and the picture written down in your notes, because if we just wrote this down but we don't have a picture to reference it to, you might look back in your notes and be like, what the heck did I mean when I wrote M angle BAC is equal to a half M arc BC? Okay, so now we're going to use that equation where the angle is equal to 1/2 the measure of the arc. So in number one, they gave me the inscribed angle. So angle ABD is 90 degrees, but we need to find the measure of the arc AE to D. And it's pretty obvious that it's a semicircle, right? Because we know that AD is the diameter. So we know that this has to be 180 degrees. But if we were to use the equation, we would need the measure of the angle, which is 90, is going to be equal to 1/2 the measure of the arc. And in this case, let's say we didn't know it was a semicircle, then we would have had to set up an equation like this, multiply both sides by 2 to solve for x, and we get 180 is equal to x. But this one was a little easier because we know already that a semicircle measures 180 degrees. So therefore the measure of arc AED is 180 degrees. Okay, now moving on to number 2. They now gave me the arc's measure in degrees, but we need to find the inscribed angle's measure. So now we have x for the angle is equal to 1/2 times the arc's degree, which is from A to D, is 196 degrees. So x is going to be equal to 98 degrees. So the measure of angle ABD, or the inscribed angle, is 98 degrees here, 98 degrees. And that is my answer for number 2. So just remember that it's the angle is equal to 1/2 the measure of the arc. So that's the theorem that we want to remember. Okay, let's do one more example using this theorem. Remember, the theorem says the angle is equal to 1/2 the measure of the arc. So in this case, my angle is 70 degrees. So we're going to plug the angle in on the left-hand side of the equal sign. 1/2 times, in this case, my intercepted arc is measuring 7 times x degrees. So that we're going to place 7x in for my arc in this equation, or this formula. So now 1/2 times 7 is 3.5x. So we're taking 70 equal to 3.5x, divide both sides by 3.5. 70 divided by 3.5 is 20. So therefore we get x is equal to 20. So this is a good example of what it would look like if we were to use algebra and this theorem together. Okay, another important theorem that we need to know is that if two inscribed angles of a circle intercept the same arc, then those two angles are also congruent. So in my picture, the angle XWZ, or this angle right here, and the angle XYZ, or this angle right here, they are intercepting that same arc from X to Z in the circle. So this intercepted arc is the same for both of those inscribed angles. So therefore, we're saying that those two angles, W and Y, are going to be congruent. So that's a little simple, easy theorem. That's sometimes hard to remember because you just forget, but it's good to know. Okay, so some more definitions. Again, these are all formal definitions in this unit, and for the most part, they're pretty self-explanatory, but just in case you were to ever hear these words or see these definitions in standardized tests, you know what they're talking about. Okay, so an inscribed polygon, or when something is inscribed, it's within the circle. So an inscribed polygon is a polygon with vertices all on the circle, but it's inside. So it's always inside the circle, and its points, or whatever we're talking about, if we're talking about an inscribed angle, then its vertex is always lying on the circumference of the circle or the edge of the circle. When we say circumscribed circle, that means that that shape or that circle is around the inside, so it's on the outside. So when it's circ or CIRC, that means around outside. So just so we know the difference between inscribed and circumscribed, because those words are definitely hard to interchange. So inside of a circle or circumscribed is around the outside. All right, some more important theorems. So if a right triangle is inscribed a circle, then the hypotenuse is always the diameter of the circle. If one side of an inscribed triangle is the diameter of the circle, then the triangle is a right triangle and the angle opposite the diameter is the right angle. So basically what we're saying is, if you're given a right angle with the point on the inside touching the circumference of the circle, then its hypotenuse of that right triangle is the diameter. And if you've been given the diameter of the circle and a triangle inside, then we know that this angle opposite of the diameter is going to be 90 degrees. It works both ways. That's what these two theorems are trying to say. So let's look at some examples using those theorems. So if PQ, they didn't say in the directions, but given PQ is the diameter, then we know the angle across from it is 90 degrees. So in order to find x, we just say 90 is equal to 3x, divide both sides by 3, and voila, x is equal to 30 degrees, or 30. And we have one more important theorem, so we're just continuing these theorems in our notebook. A quadrilateral can be inscribed or inside of a circle if and only if its opposite angles are supplementary. Remember that when we say if and only if, it works both ways, just like an equation sign. So if opposite angles are supplementary in a circle, then there's probably a quadrilateral in that circle somewhere, inscribed in that circle somewhere. And if we have a quadrilateral already inscribed in a circle, we can assume that their opposite angles are supplementary. So angle A and angle C are opposite of each other, so those two things added together will give us 180. Angles B and angle D are opposite each other, so those two things added together equal 180. So let's look at some examples with that theorem. So now we have y plus 80 is equal to 180, because this and this are opposite of each other. If we add them together, that equals 180. So if we subtract 80 from both sides, we know that y is equal to 100. And if we set up the other one, x plus 85, is going to be equal to 180. So if we subtract 85 from both sides, 180 minus 85, x is going to be equal to 95. Okay, so let's use that theorem to set up this equation to find x and y. So we have 2y plus 24x is equal to 180. And then we have 16y plus 12x is equal to 180. So 16y plus 12x is equal to 180. So what I want to do in order to solve is I have to solve using systems of equations, because if you notice we have an x and a y variable in one equation with two equations. So there's no way I could just solve for x or solve for y in just one of the equations. I have to use both of the equations, which is a system. So therefore I either need to solve by substitution or elimination. I don't know what your background is with what you like, but I personally like elimination. So I need to look at columns like vertically to see what variable I want to eliminate. So I need to multiply either the blue or the red equation by something in order to get something to cancel. So I notice that I have a 24 and a 12 with the x's. So what I'm going to do is I'm actually going to cut the blue equation, because this is the first thing I thought of off the top of my head, in half. So I'm going to multiply the top equation, or the dark blue equation, by a negative 1/2, and then I'm going to carry it down. So negative 1/2 times 2 gives me a negative y. Negative 1/2 times 24x gives me a negative 12x. And negative 1/2 times 180 is equal to a negative 90. Now, if I just look at these two equations, I can add vertically, and then my x's will cancel. So 16y plus a negative 1y, that's equal to 15y. My 12x minus 12x cancels. 180 minus 90 is 90. Divide both sides by 15. And then we get y is equal to 6. And now we have to plug back into one of the equations, 6 somewhere in for y, and then solve for x. So if I plug it back into, I'm going to plug it back into this equation. So I have a negative 6 minus 12x is equal to negative 90. Add 6 to both sides. We get negative 12x is equal to a negative 84. Divide by negative 12 on both sides. X is equal to 7. So that's just a quick review of how to solve systems of equations using elimination. I know that I explained it kind of weird, so if you have questions, you can ask me about that when you come back to class. But that is all I have for you today, so make sure you get all these notes written down, and I shall see you soon.